mind. But anyway, I'm gonna just like dive right into my presentation that I have today. Just real quick, we do have social media. We have Twitter, Instagram, have a YouTube, and the memes are actually really good on the Instagram in particular. So I really do recommend you guys to follow it. I feel like there's always like different people who come to my stream. So particularly this stream, I feel like there's a lot of new people. Have you guys met me before? Just like throwing out a question in there. Have you guys been to my Thursday streams? Because this is my first Tuesday stream right now. Have you guys seen me before? I don't think I've seen Pratish before. How about the rest of you guys? Jody, Mira. Okay, I'm gonna assume that means that you guys haven't seen me before. So I'm gonna just like go on like a really quick overview of who I am. So my name is Casey Lee. I am a hold on, I just saw some more chats. Oh, okay. But anyway, I'm gonna just introduce myself really quick. So I am a current sophomore in university. I go to Columbia University to do mechanical engineering and potentially electrical engineering. So I'm either going to be a mechanical engineering major with electrical engineering minor, or an electrical engineering major with a mechanical engineering minor. But like all in all, I'm just a person who really enjoys physics. I've taken the AP Physics 1 test before, so like I'm experienced in this type of physics in particular. And you guys don't need to worry that I've forgotten all of my like physics knowledge, because I'm taking the exact same physics courses but at a higher level in college. So I think that I am pretty well aware of like most of the content in AP Physics. Also, just a quick plug. I usually don't do these types of streams where I just like lay out a bunch of slides and like directly teach you a lot of content. What I usually do is I do practice problem solving every single Thursday. So those are personally my favorite types of streams, because what I usually do is I just like sit down and like I let everyone bring in their physics questions, and I just sit down and try to conceptually understand these questions and demonstrate how to use like mathematics to solve a lot of these problems. So like basically it's just a day for you guys to come in and just see how to like solve certain problems. Like if you have personal questions from like your physics homework, I'm willing to like teach you how to solve them. If you have like a concept from your physics test that you don't understand, or a physics problem you didn't quite able to answer on the test, I'm like available to go over it. So it's basically a free hour of like practice. And if you guys don't have enough questions, I also do a lot of like practice problems that I usually make up on my own every single week. So just a quick plug, I usually do it Thursday nights at 9 p.m. So yeah, you can just swing by and talk about physics. I usually just like fangirl about physics for like an hour and just talk about really cool graphs. But yeah, feel free to drop by on Thursday night. Okay. So in this stream in particular, so this week's theme, I believe, is projectiles. So what I'm going to focus on is horizontal launch problems. So that basically means that you're only having like an x form of velocity, like x form of initial velocity in your problem. And so first I'm going to like introduce a basic problem, and then I'm going to introduce equations, and then I'm going to demonstrate how to solve the problem. So like the personal way that I enjoy learning is that like I don't really understand if I get a straight lecture. Like if you give me a problem to solve and then you like I sit down and go through the steps with someone, I feel like that's a lot better way of understanding the concept and like understanding how to do the problem in and of itself. So that's I'm basically teaching the way that I personally think is the best way to learn. So start with the question. Okay. So I kind of just like made this problem up. I couldn't really think of like many situations where you would have like this like strange velocity problem where it's not like the really basic guy on a cliff throwing a baseball. So I made up something on my own. So I was taking pictures of some mountains in my car with the windows pulled down, and my phone with with my phone outside of the window. Suddenly my phone fell out of my hand. Or traveling 80 kilometers per hour and my hand was a meter above the ground. How far away did my phone fall from its original release location? So first off, like we need to like collect all the really basic important information, right? So we're given that we were traveling at 80 kilometers per hour, right? So that is analogous with like an x velocity in the x direction. My hand was a meter above the ground. That gives us like knowledge of the y displacement above the ground. So we have like two values already, and that's already pretty good, right? How far away did my phone fall from its original release location? So we're trying to find t, not t. Well, we will need to find t, but we will need to like find how far away, so the x displacement, right? So yeah, what do you think? How do you guys think you should solve this problem right now? Like, how would you approach this problem? Just like throwing a question out into the audience. Anyone want to say how you would solve this? Anyone? It's okay if you guys don't have anything to say because it's kind of my job to teach. But if you guys have like any idea how you would first approach this problem, like if you were sitting down on a test right now, how would you approach this problem? Anyone? Okay, if no one's gonna say anything, I'm gonna just go straight ahead into like how I would personally solve it. Because there's definitely a lot more ways to solve a problem than what I'm doing. But anyway, I listed out like all the things that you could possibly gain from this information. So we know y acceleration, just something I forgot to mention, which is universal in all drop problems, right? So in physics, you're going to be faced with a lot of different types of drop problems, albeit like launch problems vertically, and where it's like being pulled down by the acceleration of gravity. And then like, you're going to have like just straight drop problems where you like, don't have an initial upwards velocity. You can have like one of these problems where you only have the x velocity initially. However, all of these problems have the similarity that there is a y acceleration, which is 9.81 meters per second squared. And that is just like a general constant you pretty much need to memorize. You can derive it by like solving for like the gravitation equation, which is not currently relevant, but you just need to know that y acceleration is 9.81. And remember that we are given that constant. X velocity is 80 kilometers per hour and y displacement is 1 meter. Right? So these are just things I've talked about earlier inside the stream. Okay, so just a quick FYI about these types of problems. So what really sets these types of problems like separate from typical launch problems where it's just vertical displacement? There's a horizontal displacement. So when we think about projectiles, the x component and the y, well, the x component and the y component are two completely separate values that are completely disconnected, other than by the variable of time. Right? So I feel like this is a little bit confusing to understand first, but this is primarily because of the idea of vectors. So have you guys learned about vectors in school before, or you guys like know what a vector is? Just like throwing out a question, just so I understand how much knowledge I need to go over. That's really good. Vectors are really important in physics in general. So you know like the vector notation, right? It's always like an x like magnitude and a y magnitude, right? And the reason why vectors are so effective is because no matter how great like the x component is, if you think about like the x and the y components, right? They're completely like perpendicular to each other. So no matter how far you go into like the y displacement, it will not contribute anything to the x displacement. So basically, you know how like parallel lines, they never touch because they're like at a complete like 180 to each other. They're never able to touch. Like it's kind of the same concept when we have like x and y components, right? The x and the y are completely perpendicular. So no matter how long they go, one will not contribute to the other. So they're basically existing in two completely different dimensions that we completely separate other than with time. And that's why vectors are so powerful inside physics, because and like general mechanics and even mechanical engineering principles is because like x and y, no matter how complicated a vector is, you can separate into x and y, which will not contribute anything to each other. Does that make any sense? Like I don't want to like explain something and like have you guys get lost, because I feel like that can like frequently happen. You guys understand what I'm talking about? I'm gonna assume that's a yes. I'm gonna continue. So the way that I personally would approach this problem is that I pull up my handy dandy equation sheet. And as you guys know, in AP Physics, you guys are all given this nice equation sheet, and all of the equations are directly on your equation sheet. So you don't need to like derive anything. However, I heavily recommend you to learn to derive these equations. But because I was talking about vectors earlier and you can solve x and y separately, like you can solve for time in one component and it'll apply to the other, right? So what should we do? Like, do you guys have a guess on which equation we should use first? Anyone? Come on, guys. You guys can like drop stuff in the chat. I know you guys are out there. Which equation do you guys think would be best suited for this type of problem? Anyone? Anyone know? Just for like the new people who are here. Like we're talking about a horizontal launch problem. And we're given these three things. We are given the y acceleration, which is 9.1, which is not necessarily given. We're given an x velocity, and we're given a y displacement. So how are we going to connect these two equations? Like what equation are we going to use first? Anyone want to say anything? Anyone? Okay. I'm going to just assume that you guys already understand. But what I personally think is that you should use a second kinematics equation to solve for y displacement. But yeah. Okay, hold on. Something that you need to notice about our problem is that the units are kind of weird, right? So we have kilometers per hour and our y displacement is in meters, right? And that's like what trips up a lot of people at a really low level. Like even like people at higher level of physics can get tripped up by like simple unit conversion. So before you actually start solving for anything, you guys should solve for units first. So if you want to go back, do you guys want me to like actually solve for like kilometers per hour? I can pull up like an MS Paint canvas and just okay. If that is helpful, I will definitely do it. Let me pull up my MS Paint canvas. Okay, so this is kind of how I usually do my my Thursday work sessions. I just pull up a blank canvas and we just bang out some questions. So let's see our original question. So we have, hold on, let me use snipping tool so I have all of the equations available to me. Yeah, just a moment. Copy and paste. So we know y acceleration, x velocity, and y displacement. So for now, okay, let me use like the correct colors. So for now, let's solve. We actually know a lot more about y displacement than the problem that's on, right? So the y displacement is basically just this very, very simple drop problem, right? So the y initial, the v initial for the y is going to be 0, right? Because when I'm like in my car and I'm holding my phone, it's not dropping in the y direction. The y is constant. So v initial for y is going to be 0. And the v final is something we don't really know, right? But does this really matter though? Like in the kinematics equations, there's a lot of equations that doesn't require v final. Let me pull up the let me pull up the equations. So kinematics equations are not pulling up. Let me just like hand write it. So x final is equal to x initial plus v initial times time plus 1/2 at squared, right? So this is just like the general kinematics equation that like we use for one of our concepts. And I actually derived this equation very well in my first stream. I think it was like September 3rd that I gave a very thorough derivation that is heavily based on calculus, or if you don't understand calculus, simple graphs. So this is just like a simple equation that I like to use. And once I see a drop equation, like I automatically go to 1/2 at squared. And I know that because because x and x final minus x initial is just going to be delta x, and v initial is equal to 0, and that's just 1/2 at squared. So delta x, well, in this case, it's delta y, is going to be 1 meter equals 0 plus 1/2 at squared, right? So originally I was talking about units, right? So we have kilometers per hour and 1 meter. And I think I personally feel like everything is really nice in meters per second, right? Because that's just like generally how we use. Like it's a typical SI unit. Like the base SI unit is meters and seconds. So I might just keep for now. I like the way this equation looks, right? I want meters. I think acceleration's in meters per second squared, so that's already good. And t is in seconds, right? And like once again, I like to check whether or not my units cancel out. So this is 1 meter is equal to 0 equals to, not equals to, plus 1/2 acceleration, which is in meters per second squared, times second squared. If you cross out all of the seconds squared, you get meters is equaling to meters. And that means I know something is going right, because if I multiply all of this out and I have meters is equal to seconds, I know that I'm doing something very wrong. So anyway, going back. So we know that 1 meter is equal to 1/2 9.8 t squared, right? So this is just 2 over 9.8 square root. That's just like me jumping a couple algebraic steps, and that's going to be t in seconds. We want to be very careful with units at all times, because you don't want to like solve like a really complex like physics problem and be like so proud that you finished it and you solved everything correctly, except everything was in kilometers rather than meters, and you get the entire problem wrong, and it sucks. And you don't want that to happen. So might as well always stay on top of your units, because they're so incredibly important. Let me actually solve this really quick. Let me just chuck this into a calculator. Let me see. 2 divided by 9.8. Let's see. I actually, in college, I don't use graphing calculators anymore. They don't believe in calculators. But anyway, I solved t to be 0.45 seconds. So we kind of want to hold that to the side. Oh, it's ugly. So I'm going to have t is equal to 0.45 seconds. All right, you guys see how I got there, right? I don't want to like lose you guys. You guys got that? You guys know where I'm at? Okay, I'm gonna just continue. Okay. So I feel like I should go over like the basic concept of like how to. Hold on. Let me go back to my slides. Chrome pad. Okay. So basically, what I just did was 1/2 AT squared, right? And I feel like this is an equation you should memorize in your head personally for drop questions in general, because it's simply so convenient. And I have a really good description of it in my 9/5. Yeah, 9/5 stream. So that's like a very thorough derivation of it. Basically, if you understand that the area under the velocity curve is going to be the displacement, and that like assuming that A is constant, you can tell that like the I can like give a really brief description of it, but you know that velocity final is going to be acceleration times time, and velocity initial is just going to be 0. So if you find like the area under the curve for this graph, you just have acceleration times time times the base of the triangle, which is just time. You multiply that together to get AT squared, and because it's a triangle, it's 1/2 AT squared. So that's just like a really, really quick overview of how you derive that type of equation. Let's see. Let's get my last. So we are solving the t variable. So that's what I just did. We were missing the t variable, and the t variable is ultimately what connects the x and y displacements, not displacement, like the x and y kinematics. So we just ultimately solve t for vertical kinematics, and that's just how we solve virtually all types of drop problems. Just we use 1/2 AT squared, and we just, just go through the problem. Okay. So we just got time from our last equation, right? So what equation should we use now to solve for the rest of the kinematics? I feel like there's like not a lot of people left. Jody, Alvin, you guys want to say anything? You guys don't want to interact. That's okay. I know it's kind of weird to like see some stranger on the internet, like just talking to you and saying that you should put stuff in the chat. But now that we solved for time, what kinematics equation should we use? Anyone know? I feel like this is a little bit of a trick question because, I mean, is it really a kinematics equation? I don't even think it's on this equation sheet. That's the thing. You guys have any ideas? Just really quick. Okay, I might just assume that like you guys are just a little bit quiet. But we have velocity. We have horizontal velocity, which is x velocity, and now we have time, and we're trying to look for the distance. It just sounds like a really simple, yeah, distance is equal to velocity times time, right? And I want to go back to the units thing, right? Let me see if I can go back to my paint canvas, right? So you have distance is equal to, let me see if my paint canvas is up. Yeah, distance is equal to velocity times time. And once again, distance is in meters, velocity is in meters per second, and time is in seconds. And that's just really simple, like cross out, and meters is equal to meters. So you're solving for meters by getting rid of the seconds inside the velocity. And you can do this for a lot of things. Like if you solve for like velocity is equal to acceleration times time, meters per second equals meters per second squared times seconds. You just basically get rid of one of the seconds, and that ultimately becomes velocity. That's like kind of a more intuitive way of like making sure you're doing things correctly, and also understanding why these types of equations work, right? So it's just really basic. Distance is equal to velocity times time. I don't think that this is extremely hard, but also x velocity is currently in kilometers per hour, or we want meters per second, right? So let's do some dimensional analysis to finish up this problem that we have right now. Let's get a thicker size because I feel like this is looking pretty skinny. 80, just crossing out your units is such a good habit to have, honestly. So let's first try to cross out hours. So 60 hours. Okay, I feel like, the distance equals velocity times time equation is basically like dimensional analysis to me. Like it's like the same thing. 60 hour, no, not 60 hours. It's 1 hour per 60 seconds. And 1 kilometer is 1,000 meters. Right? Did I do anything dumb yet? No, I did not do anything dumb. Okay, so that's going to be 80,000 divided by 60. So it's going to be 8,000 divided by 6. Let me just type that into the calculator real quick. 1,333.333. And that's just repeating, but let's say that we care about significant figures. Personally, I don't really, but let's say we do. So we know that this 1 kilometer is just like a constant that's given to us, so that doesn't really count. So the next thing that we really have is these 2 sig figs, which is like what we're given, and that's just 2 sig figs. So there's 1,300 meters per second. Wait, this does not look right. Hold on. That looks a little bit too fast. Kilometer, hour. Meters per second. I feel like that's going way too fast. Jenny, are you out there? This is definitely, I'm doing really basic dimensional analysis incorrectly, I feel. Hour. Oh, because I forgot about minutes. Yeah. Okay. I'm being a fool. I forgot that like minutes were a thing. So 60. So 1 minute, 60 seconds. Yeah, I do a lot of dumb mistakes like that. So you just divide that by 60. Yeah, that's gonna be 21. Where's my cursor? 21.66666666. Repeating. We want 2 sig figs, so let's just say that's 22 meters per second, right? So 22 meters per second times 0.45 seconds. You cross out the seconds, you only get meters, and that's just gonna be 22 times 0.45. It's gonna, hold on, my calculator didn't go. 9.9 meters. Yeah. If it goes at like, so 1,333 meters per second implies that it's going 1 kilometer per second. That's a little bit too fast. That's like saying I can run a 5K in 5 seconds. That'd be like really dangerous if that were happening in real life. But yeah. Yeah, basically this is 9.9 meters, and once again, it's very good to see that intuition. 9.9. So basically what's happening here is that you have like the forward velocity of the car, and like because that there's nothing like hindering that forward velocity, it just continues to travel before it like drops. So there's like that upward normal force that you're applying on your hand, and you let that go, and you allow the acceleration from gravity to go down. So it just goes, it moves to the right 9.9 meters, whereas your car is just gonna continue on without it. So yeah, this is just how you solve one of the kinematics problems. Yeah, definitely. Just like being very intuitive. I remember I was doing my physics final, like my actually my last semester. So my second semester in physics, we were doing some sort of thermodynamics, and we were calculating how fast like this ice plate grew. So like we had like this bucket with ice in it, And for some reason, my calculation came out that my ice was growing at 60 kilometers, not 60 kilometers, like somewhere like too absurd, like 60, like 600 like kilometers per second. And I was like, that is definitely wrong. Like, I'm pretty sure that ice doesn't grow in your bucket at 600 kilometers per second. Like, and I sat there and I couldn't figure out how to solve it any other way. So I just kind of left it there. But yeah, it's good to just see whether or not something is wrong. Anyway, I'm gonna go back to my slides. Let's see, application window, share. Okay, let's see. So we're back to these equations. Yeah, so that's pretty, I think that's like really simple, right? Like it's pretty straightforward. So you have like the y and the x components that you want to solve for. And like obviously it's a lot easier to solve for y first and then solve for x because y is just a simple drop problem. So this is just me fielding out question. I expected this to like, I didn't expect this to take the entire session. So I'm not surprised that I'm only like 35 minutes in. But if you guys want, I can do more practice questions so I can like come up with even more stupid questions for us to do. Or if you guys have any general physics questions, I'm willing to answer those. So you guys, if you guys don't have any questions, I'm gonna default to just do more practice problems that I make up. So you guys have any questions about like kinematics in general? Anyone? Let's see who's on the stream right now. 4 people on the stream. Okay. Do you guys have any general like physics questions? Hold on. Anyone? Just making sure. Okay, if like no one's gonna say anything. Okay, so like if I'm in the middle of solving problems and you guys have a question for me, then just go right ahead and just ask it in the chat. I'll be able to see it. Otherwise, I'm just gonna make up even like more stupid questions for us to go over. Okay. So I think I'm gonna just go straight to my paint canvas because, of course, that is my favorite. Okay, you guys see that? Paint canvas. Okay. So the other day, I was on Khan Academy to like, try to find some sort of inspiration for creating these strange like horizontal velocity problems. And they were like, yeah, so what we did is that we had a drone, right? And I was like, wow, that's pretty cool. We got a drone going. It's just flying above us. I don't know what drones look like. I think that's a drone, and you have like the center like modem thing. And it like has like a package, right? That's a package. Yes. Okay, so this guy's flying by. What's like an absurd speed for drones to fly at? I hope they don't go as fast as cars. Let me think. Let's say they go at like 3 meters per second. That sounds not reasonable actually. Let's say they go 1 meter per second. That seems pretty fast. And you're like, let's say you're down here. Okay. Let's find a problem. Okay, I want you to solve for, let me just figure out a variable I want to make you guys solve for, but we haven't done that yet. So earlier we just solved for distance. What else can you really solve other than distance? Okay, I might just assume that we keep on doing distance, right? So you're down here and you wanna catch the package right before it like falls onto the ground, right? Because I don't know why you would want to do that. And let's say that this guy is like 30 meters into the air, right? And it drops like, let's say this is like 40 meters. Okay, so let's say that we drop the drone, drop a package right here, right? So we're gonna see, we want to know what distance you want to, how far forwards or backwards you want to run in order to catch the package, right? So first we have this typical drop problem, 30 meters, right? And once again, I love 1/2 AT squared. It's just so simple. Just do 1/2 9.8 T squared. So simple. You use 60 divided by 9.8. Square root that is equal to T. All right. 60 divided by 9.8. And so it's 6.122. 6.122 to the 0.5. 2.47. So T is going to be 2.47 seconds. So if it's going at 1 meter per second, right, and it has 2.47 seconds to move to the side, it's just going to be distance is equal to velocity times time. So distance is equal to 1 meter per second times 2.47. Well, this guy should have been a lot closer. So this guy needs to travel 40 minus 1.247. Oh, we can also calculate the velocity he should run. We can add in some kinematics. So this guy needs to run 1.247, 38.753 meters. So he's over here and he sees a drop, and we want to find the velocity of how fast he should run in order to get the package. So once again, we have like this other simple distance is equal to velocity times time problem, but we need to find velocity. So we have 38.753 is equal to velocity times 2.47. And that's going to be 38.753 divided by 2.47. 15.68. 15.69 meters per second. Is that even humanly possible? I think that humans naturally run at like, you can probably run like a 5K in 30 minutes. So probably like a 10K in an hour. Yeah, I don't think that's humanly possible. Is it? Anything? 30. Let's see how fast this guy goes per 15.69. Oh yeah, that's definitely not humanly possible. So basically, he has to go faster than like the world record to get that package. But anyway, that's like just a different type of drop problem that we can have. Let's go back to like one of those classic launching a projectile off the cliff. You got your friend, call him Ben. He wants to throw a ball at you, right? So he's gonna chuck this ball, and he has a pretty good throwing arm. Let's say that he can throw it at like 8 meters per second if he tries really hard, and his cliff that he's standing on is like 100 meters, right? So I guess for these types of problems, you only need 2 variables, and you can solve for the rest of them. You can solve for the final velocity. You can solve for v final. You can solve for t. You can solve for distance. You can solve for a bunch of different variables by knowing 2 other variables, and I think that's really cool about kinematics. Okay, so let's go through this over again. So you have 100 is equal to 1/2 AT squared. A is equal to 9.8, right? And I guess it's like really important to notice that like 9.8 meters per second squared is in meters, right? So you need to make sure that you're calculating for meters once you do the acceleration, right? So that's just gonna be 200 divided by 9.8 is equal to t. You square root that, divided by 10. You know, let's just round 9.8 to 10, and that's about the square root of 20, which is about 2 root 5. Right? You know, I should actually like solve these numbers. I'm being like my professors. 20. 2.5. So t is gonna be about 4.57. Right? So you have like the horizontal velocity, 8 meters per second. And that's just once again a simple, it's just a pretty simple, this distance is equal to velocity times time. Let me check if I'm doing my work right. 200, 20, yeah, that looks about right. So it takes 5 seconds to drop. This is equal to velocity times time. Distance is equal to 8 meters per second times 4.57. Just round that. So let's just round that to 8 times 4.6, and that's going to be 36.8. Yeah. Meters. Distance is equal to 36.8 meters. Yeah. So that's pretty far. Let's do another kinematics problem. Okay. So, you know, are you guys still hanging in there with me? If you guys have any questions, feel free to like stop me and like ask a question. I'll be able to see it. But you know those like, you know, when you were a kid, right? And you used to play baseball, and they had those things. I never played baseball personally, so I wouldn't know. But they had those like stands, right? And you had like a baseball here, right? And you're like 8 years old or something. You're like really excited to like hit this baseball. So this is you when you're like probably 8 years old, right? And you're like, wow, I'm gonna hit this bat. This is my interpretation of what you would look like when you're 8 years old. Right? So you got this guy and he wants to like hit this ball. Right? And this guy, he's probably like a meter tall. Right? And let's say you want to get to at least 30 meters. Right? Let's see if we can solve this backwards. Right? So let's ask, what is the velocity you need? I haven't actually thought about this problem yet. So let's see if we can actually solve this. So let's work backwards. 1/2 at squared is equal to x. So you have 9.8 is, I should probably write everything out. 1.1/2, 9.8 t squared equals equal to x. So right now we're just solving basic drop. So let's assume that you only hit it with like a force in the x direction. So you only accelerate it in the x direction. Oh, I have a question on a homework problem I had recently. Try to answer by plugging in the numbers and solve it quickly, but deriving an equation first. Oh, I love deriving equations. That's perfect. What we should do, yeah, no problem. I can take a look at it. If it's specifically kinematics equation derivations, those are like my favorite. So feel free. But anyway, I'm gonna continue with ourselves when we were 8 years old. So we're solving for a very basic drop problem, right? And you know that x is 1. 2/9.8 square root, which is equal to t. And 0.45. So t equals 0.45 seconds. Okay, so we know the distance, 30 meters, equals to velocity times time, 0.45. So we need to find how fast this guy needs to hit the ball, like what the initial velocity should be. So you do 30 divided by 0.45, 66.7 meters per second. And I forgot to mention this is seconds. And then you can just, if you look at how this problem is set up, 30 meters divided by seconds is automatically meters per second. The unit. I think that's pretty cool, personally. Okay. Let's see. Tiffany, take your time writing out your problem. I might just continue rambling on about kinematics equations. But, okay, let's see if I can make up a problem where you're going to need to solve for, I don't know, height or something. Let's try to solve for a problem we haven't done before. So let's say you're on like an elevator, right? You're chilling on an elevator, and for some reason, it's like one of those like open elevators where you can like reach your hand out, right? And you want to throw out your baseball. You want to throw a baseball, another baseball, once again, out of your window. And you got your buddy, like Tom. Why are they all male? Okay, let's call this person Janelle or something. Your buddy Janelle wants to catch it. She is once again 40 meters away. Speed ramp and airplane. Okay, Tiffany, I just saw your problem. I'm like not very interested in my elevator problem, so we're gonna take a look at Tiffany's problem right now. The closet space, such as the person who stands on it. Still on it, leaves the ramp 64 seconds after getting on. Okay, let's draw this out. Let's do. Okay, you guys just wait a tiny moment. I'm gonna use snipping tool, and I'm gonna take this problem and put it right on the screen. There we go. You see that? Technology, right? Let's put a nice box around it so I don't like screw around with it. Okay, a speed ramp at an airport moves at a constant speed. So you got a speed ramp and you got yourself chilling on it. Really excited you don't need to walk that distance. 64 seconds after getting on. So you got 64 seconds to span this distance, right? Clifford is in a hurry, so he skips the ramp. Wow. Sorry for Clifford. Starting from rest with an acceleration. Oh, he's accelerating. That's pretty powerful. He covers the same distance as the ramp does. But he covers... Dang, he's fast. Okay. See, this seems pretty simple. So you have acceleration, right? 0.37 meters per second squared. He covers the same distance. Oh, I can see why this is a little bit complicated. But you know how we were solving for like a bunch of different variables with only two numbers were given? We can do pretty much the same thing, right? So we don't know the distance, right? We're not given the distance. What is the speed? Oh, I see. Okay, I feel like you can solve this without actually knowing anything other than like the acceleration. You can like completely. I feel like you can disregard this 64 seconds by like thinking about this for a moment, right? So we have a times, okay, right? So you have 0.37 seconds, right? And if you were to accelerate for 2 seconds, right? You know, I should probably do this the manual way, okay? So you have 1/2 at squared is equal to x, right? So this is the displacement. But we have our own initial velocity, 0.37, right? Velocity times time, right? So you can cross out one of the velocity, you can cross out one of the time. So 1/2 acceleration times time is equal to 0.37 meters per second, right? But you know that the time, but in 1/4 of, oh, so the time is not the same. Okay. So you can say that t is 1 and t here is 4, right? So 1/2 a is equal to 4 times 0.37. Wait a second. Let's see. No, I just messed up all the constants. I'm like misreading everything, but you get the concept, right? So you have 1/2 at squared, 1/2, so the acceleration is 0.37 meters per second squared. And then you have t, right? So you have t 1/2 a. So the t, the time it takes for you to go this distance is 4 times less, right? So that's 1 t value times t, and this is equal to distance is equal to velocity times time, right? So you have a velocity that we don't know yet, but we want to solve it, and you have t times 4, right? Let me see. Yeah, so basically what I'm doing is I'm setting, this is x is equal to x, right? Distance is equal to distance, right? And I mean, I don't think that really matters. It's just like get rid of the t because we can like plug in numbers for all we want. So let's say it goes for 1 second, 4 seconds, and we can solve for 1/2. Let me just plug in the numbers, see if I'm actually right. So I don't want to like mislead you on anything. 0.37 divided by 2, 0.185. 0.185 is equal to velocity times 4. 0.4 is, what was your answer? Do you have the solution? Because I got 0.046. Do you have the answer? Because I don't want to like mislead you. Like I don't want to like assume that I'm doing something correct, and then like put you in a wrong situation. But do you see what I'm doing here? Oh, 0.074. Did I misread it? 64 seconds. Oh, yeah. So we can, oh, that's because I plugged in a random number, right? So 64, the number 64 is very relevant. I just plugged in 4, and I was like, that was just me being me. Okay, 64, and you have 4 times 64. So you plug in the t's, 16, right? So that'd be 0.5 times 0.5 times 0.37, 0.5 times 0.37 times 16 squared, 47.36. 47.36 is equal to, you know, I divided that by 64. 0.74. Yes, that is the correct way to do it. Sorry about like assuming that I can plug in a random t. That was just me being stupid, but you see what I'm getting at, right? So I knew that distance wasn't something that I had to solve, right? So I just set 2 equations that solve for distance equal to each other. So I don't even need to solve for distance in the first place at all, right? So I completely neglect that variable. Yeah. Oh yeah, yeah. I feel like a lot of these problems, I was actually given a very similar problem, but like two cars braking, and I didn't know how to do it on stream. But I think it's a lot easier if you can like find situations where you can cancel out the distance. But yeah, I think that's how I would solve it personally. And I think it's pretty useful to like conceptually understand the kinematics equations. So I don't need to like labor over like which equation to use. Because like when I saw this, I knew that like if velocity, like if you have constant acceleration and your velocity initial is 0, you can just straight use 1/2 at squared. That is my personal favorite kinematics equation. And then you just do equate it to velocity times time. Okay, so at least I did something right this time. Not initially, but okay, let's get rid of everything. Anyone have any last questions? I know it's 10, but anyone want to know anything about physics? I don't want to say that. Okay, anyway, I think this is going to be the end of my stream, but just an FYI. So most of the last bit of this practice was just me solving problems, just me throwing out as many random problems as I could and just solving them. And that's how my Thursday practice is kind of set up. What I usually do is I just take your problems, I solve them on screen, like what I did for the last one, and just like see if I could solve them. And like, of course, I do make mistakes. I'm a human being. I'm just like a college student, you know, just like trying out problems. So I'm not perfect, but I'm always here to help solve your problems. So Thursday night, 9 p.m. Eastern time is my usual stream time. And yeah, I just kind of enjoy sitting down and working out physics problems. So yeah, no problem. If you guys want more help, come back Thursday night. Because yeah, I purposely wanted to stream Thursday night because I always feel like homework is due Friday night or like tests are on Friday night. So if you have any last second problems you need to solve Thursday night, I'll try to help you guys. But anyway, for now, I'm a sign now. I have some other homework to do right now. But yeah, I'm glad to see you guys all showed up. Anyway, I'm gonna head out now. It's nice to see you guys.